Hello, this is Mr. Henry, and welcome to lesson 6.3, linear and non-linear functions. The central question says, how do I determine if a function is linear or non-linear? Okay. Did you know there are many situations when something is not increasing or decreasing at a constant rate? Rate is slope. In these situations, a non-linear function can sometimes be used. An example, if an object's height after being let go. So if you ever let go of an object, it does not just start falling down at the same rate. As gravity starts affecting it, it falls slowly and then faster and faster and faster. So if you ever watch, like when you throw a football or something, if you have a video of that, you know that like if you throw it, it goes up, 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 and it slows down. It doesn't get any higher, and then when it starts falling down, it falls down like that. So sometimes it's not linear. Your grade over the course of the school year is not going to go like this. Hopefully you don't start at 0. It's kind of goes up, and it goes down, and it goes up and down as new assignments are put in. Okay? The money in your bank account. You spend money, you make money. You spend money, you make money. Hopefully you end up making more money than you spend, so your money can kind of have a positive trend, but it's not linear. Okay? So our two vocab words here are linear function and non-linear function. So a linear function is just that. It's a function whose graph forms a straight line, and the slope remains constant. A constant slope, a constant rate. Those are the same thing. So if you need to make a pretty picture of it, draw a pretty picture of it. Boom. That is a linear function. A nonlinear function would then be, well, the opposite. A function that, when graphed, does not form a straight line. It can be increasing or decreasing, or both. It can sometimes do both things. So you could have, there you go. You could have things like that is nonlinear, but it's decreasing. This is nonlinear, but it's increasing everywhere. Or you could have boom, 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 boom. It's nonlinear, increasing, decreasing, increasing, decreasing. Okay, so there's a variety of non-linear functions. Linear functions come in two varieties. It either goes up and it's increasing, or it goes down and it's decreasing. I lied. You could also have one that's more like this, where it's constant. It's not increasing, it's not decreasing, it's kind of horizontal. You can have that as well. And in case you're questioning in your head, wait, Mr. Henry, what about if you have a line that's like this? It's vertical. If you remember, that is not a function. This does not work. He is not a function. It does not pass the vertical line test. And all my graphs I made down below all pass the vertical line test. They are all functions. Vertical line, vertical line. They all pass that vertical line test. Okay? So no circles going on here. Example 1. Each relation shown is a function. Is the function linear or nonlinear? If it is linear, identify the slope and the y-intercept. Okay. So it is a function. We have to determine if it's linear or not. And if it's linear, find the slope and the y-intercept. Fair enough. Now, with an equation, like this first example here, our goal is basically to see, can we take this and make it look like that? We know from experience that this is the equation of a line. This is slope-intercept form. That's a straight line. You cannot write curvy things and put it in this form. So if I can take this equation and make it look like that equation, well, then it's linear. So to do that, first thing I'm going to do is I'm going to try to get this y variable by itself. So you see it's y equals I want to make this y equals. U need to go away. So I'm going to subtract 2x on both sides. Y equals, I cannot combine these guys because they are not like terms. So just negative 2x minus 15. And I see, is this slope-intercept form? Y equals mx plus b. Yep. So this is linear. I know that because it is in the form of a straight line. My slope is negative. My y-intercept is negative 15. In fact, actually, we right here, find the slope and intercept. So I guess we should do that, huh? So slope and y-intercept. My slope is negative 2. My y-intercept is negative 15. And I know that because in slope-intercept form, this guy is the slope. The b is the y-intercept. So the y-intercept is negative 15. The slope is negative 2. Okay? So you might be asking, well, what equations would not fit into this form? Usually the equations that would not fit into this form, that don't look like this, are equations where your x has an exponent on it, or your y has an exponent on it. Those are things that would not be linear, or even sometimes actually not functions. Okay? Y equals, well, x squared is nonlinear. This is what a nonlinear function looks like. Even if you put like plus 5, because it has this exponent on it, it is nonlinear. And that could be a 3, a 4, a 5, a 6, a 7, a 12, a 97. It doesn't matter what variable or what exponent the x has, it will not be linear. Now, there are times where if you put an exponent on the y, sometimes it will be a function that's nonlinear. Sometimes it will just be not a function. But we're not going to get too deep into that right now. Letter B. We're looking at this function here, and we have to decide if it's linear or not. Well, I don't really have to think too hard about this. So this is clearly nonlinear. And the reason I know that is it is not a straight line. Non-linear, not straight. Linear, straight line. So this is not a straight line. It is nonlinear. Done. I don't actually have to do anything else to this problem because, well, there's no slope. Because it's curvy, the slope's not the same. The slope right here is different than the slope here, and slope there, and there, and there. In every place, the slope is different. Letters C and D. Okay. So, in both these problems, you see we've got tables. So, how would we find out if they're linear or not? Well, if you remember from our vocab words here, a slope is linear if the slope remains constant. If the slope is the same everywhere, that's the constant means same. On my graph here, the slope here is the same as the slope here, is the same as the slope here. The slope is the same everywhere on here, the slantiness of the line. On my curvy, the slope here is not the same as the slope here. Look, they're at different angles. Okay? Slope is the same. Slope is the same. The slanty is the same. The angle is the same. Slope is the same. So if I go back to my tables, I've got to find out, is the slope the same everywhere? So if I find the slope a couple different times, if I got the same slope, it's a straight line. If I got a different slope, well, it's not a straight line. So I'm going to use my slope formula. I'm going to use that m equals y2 minus y1 over x2 minus x1. That is the slope formula. That is how you find slope from a set of points. Like this. This is a set of points. May not look like it. You go, oh, that's a table. Yeah, but that is saying the point -3, -8, -2, -5. X value of 0, y value of 1. X value of 1, y value of 4. 5, 16. This table is just giving us a set of points in a table format. So as always, you can pick any 2 points you want when you find your slope. It doesn't matter which 2 you pick. I'll be honest with you, I guarantee you I'm picking this as my x1, my y1, because those guys are nice, pretty numbers. Why pick the ugly guys when you could pick pretty numbers? x2, y2. I'm picking the numbers that are positive. It's going to make my math easier. So when I plug it in, y2 minus y1 over x2 minus x1. You should have experienced doing this by now. Do the math. 4 minus 1 is 3. 1 minus 0 is 1. So I found between these two guys a slope of 3 over 1. Now, I need to find the slope again. Finding the slope once is good, but it's not going to answer the question for us, because if the slope, right there, the slope was 3. If I find the slope at another place, and the slope is also 3, then it's a straight line. If the slope is something other than 3, well, then it's nonlinear. So I'm going to find the slope. I'll be honest, I'm going to pick those 2 points again because they're both positive. So x1, y1, x2, y2. I'm still using my formula here. I have it written down. y2 minus y1 over x2 minus x1. 16 minus 4 is 12. 5 minus 1 is 4. And before you go off and say that these guys are not the same, don't forget to simplify. 12 divided by 4 is 3. So this had a slope of 3 over 1. That had a slope of 3 over 1. The slopes are the same. This is linear. This is linear. So I found the slope was the same everywhere. So this graph is linear. Now, I could go through and I could find the slope here, and I could find the slope here, and I could find the slope between this point here and this point here, and just all these different combinations. And we're going to find the slope is the same at all of them. The slope is going to be 3 over 1 everywhere. Okay? But now that we found the slope, unfortunately, we have some more work to do, because the problem said if it is linear, find the slope and find the y-intercept. So it was linear, so now I have to find slope, and I have to find my y-intercept. Okay, well, slope. Well, slope was easy. I found the slope. The slope was 3, or if you put 3 over 1. That's my slope. Y-intercept, well, maybe a little trickier. Now, I will tell you, the y-intercept is actually given to us in the table. If you imagine making a sketch of this, and I plot some points, I'm just sketching. 0, 1, 1, 4, 5, 16, -2, -5, -3, -8. Whatever, right? The y-intercept is right there. It's always going to happen when the x value is 0. So my y-intercept is actually the value 1. That's where my line crosses the y-axis. So I found this line is linear because the slopes are the same. I found my slope. I found my intercept. The y-intercept happens when your x value equals 0, which is this point right here, so the y-intercept is 1. Or I made a little pretty sketch, and I saw that's where it crosses the y-axis. Now, let's actually use this idea for a second here. So in this last problem, I made a sketch, and you can see that my sketch, it's pretty linear, right? What happens if I make a sketch over here? Can I do that to answer the question for me? I don't know. Depends on how accurate your sketching is. So, I mean, I'm going to start with these 2 points here because they're quick. So, -2, 0. I should change color. -2, 0. 0, -4. Okay, so I did these 2 points. 3, 5. 1, 2, 3, 1, 2, 3, 4, 5. 5, 21. 5 would be out here somewhere. 21 would be way up here somewhere. I mean, look at this. Can you draw a straight line through those points already? No. No, you can't. I did this one. 4, -4, 12. -4, 12. I don't even know what this graph... I mean, this graph is like... It's doing something like that shape, I guess. I mean, if I had to connect them from left to right, that's what it would look like. So, right now, I can clearly say this is nonlinear. I could do that just for my sketch. That sketch could save you a lot of time if you can make a sketch of it. Now, what if you didn't make a sketch? Well, then you have to go back and you have to find slopes at places. Very quickly, I'm going to find the slope of here, and then I'm going to find the slope of here. So I'm going to use this as x1, y1, x2, y2, and then in red, x1, y1, x2, y2. Okay? So in blue, top one, I'm using this formula here. y2 minus y1 over x2 minus x1. That gives me -4 over +2, which is a slope of -2. So right there, these guys have a slope of -2. In red, same formula. y2 minus y1 over x2 minus x1 gives me 16 over 2, which is a slope of 8. Did I get the same slope everywhere? No. Which means this is it's still nonlinear. I mean, we proved it using the graph. Now I proved it using the math. Found the actual slopes at 2 different points, and I found they are nonlinear. Okay? Letter E. It says, or E and F, it says they're both functions. Is it linear or nonlinear? And identify the slope-intercept if it is linear. Okay. So let's see here. Well, letter E. Do you remember what we said before back in, I think it was example A? From an equation, if you can make it look like this, that would make it linear. And after the problem, we talked about how the way you could make something nonlinear is if your x variable has an exponent, like that. This, I can guarantee you right now, is nonlinear. And I know that because that exponent. If I would go through, and I would, even if I try to solve this for y, and I add 4x cubed to both sides, and I get 2y equals 4x cubed plus 16. And then I divide by 2 on both sides. I get y equals, that's a 2. And I get y equals 2x cubed plus 8. It is still non-linear. If we go to Desmos here. Oops, that's not Desmos. We go to Desmos. And I hit Start Graphing. And I type in y equals 2x to the 3rd power plus 8. It's nonlinear. Look at it. It's got this little curvy dude in it. This is nonlinear because of that exponent. If I would take that exponent out, can I do that? Oh. To the 1st power is the same. Linear, nonlinear, nonlinear. 4 is nonlinear. 5 is nonlinear. 6 nonlinear. 7 nonlinear. 8 nonlinear. 9 nonlinear. 1st power, or just plain old x, linear. So if you have an exponent, 'tis nonlinear. This, come on, well, whatever. This is non-linear because of that exponent. Okay? Letter F. Well, that is very, very clearly linear. I can tell from my pretty picture because it's a straight line. And because it's linear, now we have to go through and we have to find our slope and our y-intercept. So I'm going to do the easy one first. Y-intercept is 1 right there. That's my y-intercept because that's where the line crosses the y-axis. It's crossing at 1. Intercept is 1. Slope. I'm finding my points. Boom, boom, boom. Boom, boom, boom. So from one point to the next, to the next, to the next, I'm going to go down 1 over 1, 2, 3. Down 1 over 3. Down 1 over 3. Down 1 over 3. Slope is negative 1/3. So it is linear. I found my slopes. I found my intercept. We are good to go. These two are for you to try. This is letters G and letter H. So if you could please pause the video now, try these two on your own. When you are ready to continue, hit play and we will go through them together. Okay, so letter G is nonlinear. And we know that because, look at it, it's a curvy. Letter H. Did you try making a sketch first? I don't know. Let's see. 0, negative 3. 2, 7. 4, 17. 6, 27. 8, 37. See, unfortunately, my sketch is not going to be good enough. I can't say, oh, look, it's curvy right there, because maybe my sketch is just ugly. I mean, this is close enough to a straight line. It puts some doubt in my brain. So I can't just go through and straight up say this is nonlinear or linear. It looks pretty close to possibly being either. So now that I've kind of made my guess and it didn't really work out for me, now I actually have to go through and do the work. Okay, so the way we're going to do it is we're going to have to find slope at two places. So if I find slope here and here, why not? x1, y1, x2, y2, and in black, x1, y1, x2, y2, and the formula, m equals y2 minus y1 over x2 minus x1. That is the slope formula. That is how you find slope. So starting in the blue, we have y2 minus y1 over x2 minus x1. And so I'm plugging in the points I've labeled here according to the formula, like we did way back in chapter 4. And I math here, 7 minus negative 3 is 10, and 2 minus 0 is 2, gives me a slope of 5. Okay? Down here, y2 minus y1 over x2 minus x1 gives me 10 over 2 equals, well, would you look at that, 5. So that means that these two guys are the same. They have the same slope. So this is linear. This is linear. The slope was the same. And since it was linear, we have to find the slope, which we now know is 5. Not slop, slope. And we have to find the y-intercept. And if you remember, back, well, where was it? Let me see. Here. We said the y-intercept always happens when your x value is 0. The y-intercept happens when the x value is 0. My y-intercept is negative 3. If I go back and put my ugly sketch up here, that very first point that I sketched, 0, negative 3, That's on the y-axis. That is my y-intercept. And all the other points were like up here somewhere. Okay? So slope is 5, y-intercept is -3. It is linear. Okay? Letter I. Here's another one for you to try. So your job is to figure out, is this linear or nonlinear? So go ahead and pause the video, try it on your own, and see what you can get done. When you're ready to continue, hit play, and we will go through it together. All right. So you'll probably try to take this and make it look like that. You subtracted 2x on both sides. Y equals 1x minus 5, because 3 minus 2 is 1. And you look at it, compared with slope-intercept form, you go, that looks the same. There's no weird exponents on my x. This fits into that same form. This is linear. Now, if you didn't do this first, you just looked at this and said, hey, there's no exponents, it's probably linear. I'll be honest with you, you're probably right. But from here, if you just looked at this, if I would go like this and cover the rest of this junk up, and I said, okay, cool, you found it's linear. Now, what's the slope and what's the y-intercept? You can't do that right from this equation. That's where solving, getting it into slope-intercept form, is going to come in handy. Because now we know that that's your slope, and that's your y-intercept. So the slope of this line was 1. The y-intercept of this line is -5. Applications. All right, so an airplane flies directly from Harrisburg to Baltimore. Mark writes a function to determine the height of the airplane as it flies. Is this function linear or nonlinear? Use words, numbers, or models to justify your answer. That models thing, by the way, could be like a sketch, a picture. So we want to figure out if this is linear or nonlinear. First thing I would do, honestly, is I'd make a picture. I mean, it's flying from, here's Harrisburg, here's Baltimore. Because we're talking about the height of the airplane. That's what we're measuring. Determine the height of the airplane as it flies. Do you think, wait, let's do it. Airplane, it's got this guy here, other wing on the other side. Oh, that is a beautiful airplane, Mr. Henry. So, is that airplane just going to go no, because it's not a very good airplane if it doesn't even go in the air. It's staying on the ground the whole time. It's just going to drive there. So no, that would not work. Airplane probably goes and it hangs out up here for a while, and then it comes back down. So the graph would look more like it goes up in the air, it hangs out up in the air for a while, and it comes back down. So linear or nonlinear? Well, clearly nonlinear. Whoa, that's not going to work. Okay, so this graph would be nonlinear, or the height of the airplane would be nonlinear, because it has to go up, but it has to go down. The slope is not the same everywhere. The plane's just not going to like take off and it goes up, 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 and it just keeps going up forever. I mean, they're never going to get to Baltimore. They're going into outer space somewhere. Okay? And it's not going to go flat, because it's not just going to drive there. You might as well drive yourself. So this is a non-linear height. The height goes up, the height goes down. And there's my model to justify. You can use words if you wanted to write a sentence explaining this. You could as well. Letter B. It says Isabella sketches a function that passes through those 3 points. Isabella believes that this is a linear function. Is she correct? Explain your reasoning. Now, here's how I'm going to start. I'm going to make a sketch. 5, -3. 2, 4. 11, -17. Darn. I was hoping by sketching these 3 things, I'd be able to tell if it's linear or nonlinear. I was hoping like there'd be like really weird points. Like if this point was like over here somewhere, I could go, yeah, that's nonlinear, because it'd be weird. But the fact that it's kind of like, at least they're sort of in line, doesn't help me eliminate that choice. It could still be linear, or it could still be nonlinear. So that means I actually have to do the work now. Darn. Okay, the work. M equals y2 minus y1 over x2 minus x1. We've got to find the slope. If I find the slope at two different places, I got to check to see if the slopes are the same. So I'm going to use, this is x1, y1, x2, y2. I'm going to check these 2 points. Not y2. Yes, that's what I wanted, but that's not what I wanted to write. y2 minus y1 over x2 minus x1 gives me 4 minus negative 3 is 7. 2 minus 5 is negative 3. And I'm just going to leave him like that. That's the slope of those 2 points. I could divide it and get a decimal, but I don't need to. That's just as good. Okay, I need to find slope again. So I'm going to find the slope of these 2 points. So x1, y1, x2, y2. In red, y2 minus y1 over x2 minus x1 gives me negative 17 minus 4 is negative 21 over 11 minus 2 is 9, and I bet this simplifies because those both can be divided by 3, gives me negative 7 over 3. Well, would you look at that? We got the same slope. So since we got the same slope, this guy is linear. Same slope. And there's all my work to prove it. So the slope is the same everywhere, which means this is a linear function. So is she correct? Yes, Isabella is correct. Hey, last problem. Letter C. In the space below, make 2 relations that are linear functions and 1 relation that is a non-linear function. One must be a graph, one must be a table, and one must be an equation. So in this here, graph, table, equation. Make one of these non-linear, make the other 2 linear. Go ahead and try this on your own. When you're ready to continue, hit play, and we'll go through it together. Okay. Now, the teacher and me, I'm going to do this whole problem twice. What I'm going to do, let me just draw a line here. So, I'm going to do much more than you had to do. Copy, paste, down below you go. You unlock and copy, paste, down below you go. I probably want to relock this thing. Oopsie, what did I do? I don't know. Undo. Lock? Nope, that's not doing what I wanted to do. What's the lock button? Locking. K. Oh well. Alright. Alright, so now they're not going to mess me up. Okay, so I'm going to take the whole top of this, these 3 here, and I'm going to make 3 that are all linear. So a graph of a linear function is a straight line. An equation of a linear function is something like y equals 2k plus 1. Or 2x plus 1, I should probably do. Okay, linear, linear. This is the hard one to make linear. So usually what I'll do here is just make a pattern. So if I go 0, 1, 2, 3, 4, 2, 4, 6, 8, 10. If your x's and your y's both follow a addition subtraction pattern, it will be linear. So this side's going plus 1, plus 1, plus 1. This side's going plus 2, plus 2. This will be linear. Okay? And that's actually a way you could have checked. Let's see if I go back. This guy here. This was a linear pattern. This was plus 10, plus 10, plus 10, plus 2, plus 2, plus 2. Because it was an addition pattern or subtraction pattern, it's linear. Further back, see if I can find the right problem. It was this one. Oh, whoa. Get back out of there. This one here, it did not follow that pattern very well. I mean, the numbers are kind of all mixed out of order. Like this was plus 2 minus 12, plus 2 minus 4, plus 3 plus 9, plus 2 plus 16. Now, you kind of ignored this plus 3 one because it wasn't the same. But if you look at the other, plus 2, plus 2, plus 2, minus 12, minus 4, plus 16, it wasn't the same pattern on both sides. This side, this guy over here, would follow that same pattern. So this was plus 1, plus 2, plus 1, plus 4. It's a little hard because they're kind of different, but all the plus 1s, plus 3, plus 1, plus 3. Both my plus 1s were both going up by 3. When I went up by 2, this went up by 6. This went up by 4. This went up by 12. It's actually, it's following the same pattern. Okay? So it's kind of a trick you can use to make a table, or to even check if a table is linear or nonlinear, is if there's an addition pattern on both sides. If every time this guy goes up by 1, the other side goes up by 2. Now, as far as making these guys nonlinear, well, there's nonlinear. And to make your equation nonlinear, y equals 3x squared minus 12. You just add an exponent. Now it's nonlinear. Guaranteed nonlinear if you put an exponent on your x. And to make your table nonlinear, well, you just make up some random numbers, but just make sure it's still a function. So 0, 9, 12, 18, 32, 1, negative 4, 6, negative 19, 0. There. It's nonlinear. Because I can guarantee you these guys aren't following any sort of pattern, so it's nonlinear. Okay, so when you did your problem like this, you should have had some combination of this, where you had to make 2 that were linear, 1 that was nonlinear. I did a little bit of everything to show you what yours could look like. Okay? Summary. How can you tell by looking at a graph if the function is linear or nonlinear? This has been lesson 6.3. Thank you for watching.